So in our lab module, in the lab handouts module, I put a doc and a PDF. The reason why I did that is for some of you, your PDF or your doc file may not show the equation correctly. So the PDF will show them right. But the doc is there so that if you want to grab any equations or tables out of it, you can just pull them right out of that and put them in your lab report. So let's look at the PDF. So what this experiment, the PDF goes through kind of the theory about mechanical energy, which I hope you all know at this point, which basically just says that at any time, if we have a mass attached to a spring, it has spring energy and kinetic energy. These could be zero, which is fine, but we set two different points. We set the energy at point 1 and the energy at point 2, set them equal, and we can find maybe the velocity or maybe x or whatever we want to find. And so what we're going to do in this lab, I'm going to flip to my video, and I'm actually going to stop sharing this for a minute. Yeah, sorry. Okay, whatever. So hopefully you guys can see this. So last week when we did the lab where we hung the IOLab from the force probe, you found the mass. From that lab, the original mass that you found, use that mass. If you need to do it again, just look at that lab and how we hung the force from the force probe and got the mass of our IOLab, the theoretical value the first time. And then what we're going to do is hook up this spring, and we're going to do this lab in 2 parts. The first time, you're going to pull your IOLab 10 centimeters and record that data and use that data in an Excel graph to figure out what the force constant K on our spring is, on the long spring. Once you've done that, what we're going to do is we're going to take it and we're going to pull it some distance and let it go to our hand. When we do that, we're going to take that data and get the initial position and velocity before we release it, and then after we release it, okay? And those data points, we're just gonna take straight off our graph, and you're not gonna have to do anything like, you won't have to do a second Excel graph of the motion. We'll talk about that in a minute. I want you to do 3 different ones. It doesn't really matter how far you pull it in each of the 3 trials, but I want you to do 3 of them so that you get multiple data sets to compare in case one of them's just garbage, which could happen. So what we're doing, in a sense, is we're finding, if we start with the spring stretched and the IOLab at rest, after it slides, we're going to take, when it stops, well, when the spring is no longer compressed at all, we're going to find the velocity. And so we're going to compare the spring energy to the kinetic energy. That's the whole point of this lab. So the first thing you need to do is go in and open your IOLab, make sure your IOLab's on, make sure the power's on. And once you have that on, go ahead and calibrate it. Go into here and calibrate the force. This is going to walk you through it. So if I go down to force, it says, okay, connect this, put it upside down, leave it for 2 seconds, click next. And then it tells you to, whoops, did I do that wrong? Oh, lift the device. Lift it for 2 seconds, hold it steady, hit it again. It's calibrated, all good. So now let me turn back on my camera. So in the first one, turn on your wheel and your force. And you really don't need the velocity and the acceleration. You can leave them, I don't care, but take it and you'll notice that when you hit record, down on the wheel position, if I move it at all, it'll tell me how far I moved it. So let me stop. What I want to do is I want to pull it back 10 centimeters. So if I hit record, pull it back about 10 centimeters, slowly, okay? Then stop this. Now what we're gonna do is we're gonna look at this graph. Make sure you're on Zoom. Look at this graph and try to get it when it went from about 0 to 1. So that's not great. So I went from 0 to 1 here. And this is what I want right here. If I do this, okay, what I can do now, and this is the super important part, this is the part that you have to pay attention to. Down here, there's this little arrow with a box. What this will let you do, if you click on it and go to export to CSV, it's going to export my document to what it says, in case this doesn't come up on the Zoom, is it says it's sending it to documents. I need to make sure I get the CSV file for the force and for my position. What I'm going to do now is I'm going to change my share to my desktop. So now you should be able to see my desktop. And where I'm going to go is I'm going to go in my window to my documents file. And here I'm going to go to my IOLab work files. I'm going to go to my export files, and they'll both be here. This was from earlier. So let me click on this, and here's important point number 2. So if I open an Excel document, I can take this CSV file, and what this CSV file is showing is the data point. I don't know what frame is. It seems to be the same. No, it doesn't. I don't know what frame is. Sample and time. And what I really want is if I roll down, I see that my, this is my wheel. So this is my distance from 0. So when I started this experiment, I had it at 0, and then I pulled it 10 centimeters. And what I want to collect is basically start from the data where it's at 0, and I'm talking about this column here, and go till it gets to 0.1. That's 10 centimeters, okay? Copy your data, go into Excel and paste it. And then you can get rid of, that file or that column. You can get rid of this column. You can get rid of the number column, but make sure you leave the time. So this is our time file, and this is our distance. And it might help to put X and T. Now I'm also going to go back into here, and I'm going to get my other CSV file, open that. That again, I want to collect, so once the time, if I look back at the time was 1.02. So go to where the time says 1.02. This is my time file right here, column D. Go to where it's 1.2 or whatever it happens to be for your time, okay? And go down to, I don't know where I went to. I'm gonna assume this is how far down I went. Copy this. I can close this now. And then I can paste this. Nope. Oh, I'm sorry, you guys. The time goes to 2:11, 2.11. So take my time to 2.11. And I really don't need all this top stuff, but it's okay. Make sure I get to 2.11. Copy. close, starting, close, close. So here's the important part. Oh, are you being a jerk? Yes, you are. Sorry, guys. All things are being annoying. Back to that, back to that. And I'm going to start at 1.02. So I'm going to start, I don't know, here. And go to 2.1-ish. So copy. Now let me make sure that this paste. All right. Now you can get rid of, again, delete these files, or delete those rows, and delete this. And I wrote these backwards, I'm sorry. This is T and this is X. And this is T and this is F. And now what we want is we need to graph F versus X to figure out what the force constant is. The reason why we need to do that is, if you look, the force of a spring is minus Kx. So if we graph F versus X and put a linear slope on it, our slope will be the spring constant. The problem is that when we do this, our time samples are not the same. The force samples at a different rate than the wheel does. But what we're going to do is go through and starting at, let's start at 1.1, delete everything above before it's 1.1, just hit clear constant. And then delete everything between 1.1 and the first data point that says 1.2. Clear those contents. And then do the same thing and on and on and on. I'm not going to make you sit and watch me do this, but I'm going to do it for the first few data points here. So if I move that up and do this all the way until so go down, starting at X is 0 and time of 1.1, go all the way down until X reaches the first value where it's at 0.1 at 10 centimeters. So this right here, you could probably do it this way, would be probably easier. And then, oh no, that's not what I wanted. I'm sorry. I'm being dumb. My brain's not working. What I want to do is go to each of the 1 point. So 1.4, the first time it hits 1.5 is right here. Copy that. The first time it hits 1.6, copy that. And keep doing that until you get to 1.7 seconds. Copy that. Keep going here until we get to 0.1. Copy this one. And this is a bit of a pain. This is really the only pain of this whole lab, to be honest. What I'm doing is in the time, I'm taking 0.1 seconds. So 1.1, 1.2, 1.3, 1.4. And I'm doing that for the first value that it reaches 1.1. Then I want my X to go from 0 to 10. So I keep taking these times until my X hits 10. Copy that, which I can see happens at 2.1 seconds. Okay, so then on your force, right, this is your time. Take your first data point after 1.1, clear those, and again, down to 1.2, clear those, 0.3, clear those, and on and on and on. So again, I can just go down and get the first time it hits 1.4. Or and I don't care, you can cut it, you can delete all this, you can just copy each point. Once we do this, 1.6, 1.7, and 1.8, 1.9. Where's my 1.9? Right there. So I only have 2 more values, and then I'll show you how we're going to graph this. And then go to 2.0. So I've grabbed the first data point after each 10th of a second. Dang it. I'm sure there might be a faster way to do this, but this is how I'm doing it right now. So, okay, I grabbed each for my force and for my wheel. I've grabbed the time and value for each 10th of a second from the time that the position went from 0 to 0.1, 10 centimeters. And for those values, I grabbed at each 10th of a second the force values. I want to graph force versus X. So take this and move it over. Remember that Excel is going to graph Y versus X here. So highlight these 2 rows, go to Insert, and make a nice scatter plot. And I can see that I have my force versus time graph here. Or do I? Nope, that's wrong. I always forget. So this, I actually need to do X versus Y to get F versus X. I need to do X and then F. What I want is I want an F versus X graph. Okay. So do a nice scatter plot. And now I can see this is my force. This is my X. If I put a linear trend line on here, on the new, newer Excel, you have to go here. On the old ones, there's that plus on the side of the graph. We went over that. But I have this linear trend line. Go back in and make sure that you hit your options. Turn on display equation, turn on display R value. Make sure that you don't tell it to set the intercept, leave the intercept alone. And then you can actually highlight this, go home, and bump it up to 11 or something. So you're going to want to take this, add axis labels, add a title, and make sure the equation's on there and the R squared's on here. Notice my R squared value is 0.9991, which means this thing is linear. This is a linear relationship between force and position. I can see from my my trend line, my slope, that my K is about 11.856, okay? And make sure you put a title, axes with units, copy the chart and put it in a Word document, about half a page or a full page, at least half a page though. All right, so if we go back here and we look, this tells us that our slope is our K if Y over X, right? So we know that that's our K. We found our mass from the Impulse Lab, and we've now got K. But here's a trick that you have to do. There's something called a lin-est function, and if you do the lin-est function, You can hit equal lin est. I included a video that's really good for showing you how to use this. It's really short, but essentially what you want is you want to do this. And I wish I could zoom in on this, but you put your values and you leave the third one blank, and then you end it with true. And when you do this, this gives you, an array function. Why are you not? Do I need to? Anyway, forget that for a minute. If I go back in here and I click on the video that's included after the experiment, there's a video right here that tells you how to use the linest function. If I go into this and I hit linest, using linest in Excel.
Today I'm going to show you how to do that.
Once you do this,
we're going to display it.
Okay.
Hit equals LINEST.
He shows how to put
We're going
in
to
the
select
functions.
those and hit a comma to move to the next thing.
And when you do that,
true, and then close the parentheses and hit. The way these work is that I'm actually going to select
do an array function.
A large section here, and this is comprised of 2 columns
here. That when you do this, it's going to give the slope, the y-intercept when x, when x is 0, it'll give you the intercept. It's going to give you the error associated with the slope and the error associated with the intercept. So what that means is it's going to give you the error associated with this 1.6774 and the error associated with 0.1143. What we want from this is we want this error associated with our slope. That is our delta F, our delta K. That's the error associated with our spring constant.
4 rows or 5 rows, depending on how you look at it. But this box, Command Enter as a Mac user.
Oh, that's what I forgot to do. Command Enter. You have to actually hit Command Enter to execute it on that box, but it will give you these values. You can see here that it gave him his R squared. So R squared is that. This is like a map of this array. His R squared value is 0.998. His slope is 1.677, blah, blah, blah. And this is his error. So his slope is 1.677 plus or minus 0.024. You're going to write that down, perform that linest function, and write that value for SE slope as the error, the delta K. Where are you? Why are you? That will be your delta K right here. So your mass is from last week's Impulse Lab, or do it again. And then K is your slope of your Excel graph. And delta K is the SE number on that, in that linest function. So make sure you can do that linest function. The reason why we need it is Excel doesn't give you the error associated with your equation. You need to do linest to get that error. Onto the trials themselves, if I go back to my IOLab, make sure it's turned on. I'm going to actually turn my camera back on just so you can see this. Make sure it's turned on, reset this, okay? And then what you can do is for each of the trials, make sure you start recording with it at 0. It's important so that you know that it's at 0 on the position. Pull it any distance you want, and then let it, hold it for a second so that everything stays constant, and then let it go, okay? So we're gonna stop it here. I really wanna zoom in on this part. So I really want to try to get where the velocity right before it started freaking out, because this is my linear region for the spring energy. All you have to do is at a certain point, right? It's going to tell you. So really you can pick wherever you want, but let's pick here. When I'm at 11.8 seconds of time, my force value is negative 2.724. Write those two things down. Go down here to 11.8 and write down your position value and the time. And then I would say go right before it starts to spike out and choose that. And at that point, I'm at 12.1252. My force value is 0.728 at 1 point, what was I at? 2.12. So at 2.12, my X value is 0.01. It's essentially 0 at that point. That's where all of the energy was converted of the spring was converted into velocity. So all of our potential energy was turned into kinetic energy. And you need to get the two values. So you can really actually, instead of doing that, you could use the highlight tool. Oh, why did you just do that? I don't know why this thing just decided to, oh, I do, sorry. So I can use the highlight tool and I could highlight this region and then make sure that I'm lined up. So you don't have to do the time thing. And if I go back to this, I zoom in, I can just look at, I can highlight sometime to 0. The important thing here is you want this to reach 0 and then be at that constant value. So go from that constant value to 0, and you can just compare the value of the position was at 0.17, and then it was at essentially 0.027. Here, the velocity ended up at negative, I'm sorry, the force. I'm being so dumb, you guys. I forgot what I was doing. So here on my velocity graph, I don't need the force graph. I need the position and velocity. So here, my initial position was oh, that's going to give me something bad, isn't it? Sorry, this is all new stuff, and I don't always remember what I'm doing. So make sure you're on the red line. I would go through and highlight when it first crosses the 0. Take the pointer tool and get what X is here when you're on the red line. So X is 0.039. Here it's 0.147. Here your velocity is 11 or negative 0.01. And here our velocity is negative 1.2 meters per second. All you have to do is look at those means, those values. All you have to do is write down your values, okay, in this table. So write down X, write down V at the first point. So on the X position, put your arrow on the red. I see my X is 0.17. My velocity there is negative 0.04. Then for the final value, my X position is 0.039 and my V is negative 0.122. So going back, you put those in here and here. What is the error associated with this? And this is important too. The error, the measurement error associated with X and V, if you look at your data, so notice that my X says it's 0.216 meters. That means my resolution is 0.001 meters. My uncertainties when I measure things are half the uncertainties, or are half the resolution. So my uncertainty here would be 0.0005, half of the least digit that I know for my wheel position. The least digit I know is 0.001. Half of that is 0.0005. So delta X is 0.0005. Same with V. It's 0.0005. because the least digit I know is, my velocity here is 0.031. The least digit I know is 0.01. All right, so once you have that, and you're all good on that, you filled out your data for 3 different trials. You've done this 3 times. Make sure that on your graphs you get when X cross the 0 effectively, right, for each of these. Once we do that, we've done the actual physical part of this experiment. So that should be pretty fast, other than doing the Excel stuff and getting your K constant, which is a little bit of a pain to change your variable or to fix your data. So now when we go to analysis, you know what the force constant is. You know what the uncertainty is using LinEst, right? And the linear equation. Now, in the spring constant part of it, we need, or using the spring constant data and the mass data, we need to find the energy before and the energy after. And this is important, okay? So for the energy when the mass is here with a velocity of this, its total energy is kx squared over 2 plus mv squared over 2. K came from your graph. M came from last week's Impulse Lab. X is the initial, right? X, and then V is the initial V. Put those numbers in, solve that for the initial energy, and write that here. Do the same thing for the final energy, okay? To find the error associated with this, you need to do this function, which means take the partial of the whole equation with respect to K, multiply that by the experimental uncertainty of K, which you got from the LinEst function, and divide it by this function for energy, and then square that. Same with X, same with V. For initial position and final position. You plug in here, so I've done these for you. I've done these terms in the parentheses for you, and this is what you get. In here, for X initial, you plug in X initial, you plug in X initial, you plug in V initial, you plug in M, you plug in K, and this delta K is the delta K from the LinEst function. For the X term of your error, multiply K by the X initial. This is the X initial, this is the V initial. This is the uncertainty from the resolution, half the resolution of the graph, which is 0.0005, right? Same here with V. V initial, X initial, and this is the uncertainty associated with that V on the graph, 0.0005 meter per second. So once you do these terms, square them, add them all together, take the square root, multiply by 100%, and that gives you delta E, the error, experimental error associated with E at the initial time and then at the final time for the 3 different experiments, okay? Then what I want you to do is once you have the initial energy and the final energy, the actual computed values from here, I want you to do the percent difference. So take the initial energy minus the final over the initial plus the final divided by 2. Take the absolute value of this and then multiply this by 100%. And that gives you your percent difference. If those are 0, then we know mechanical energy was conserved. If they're not 0, then there was something else going on. It could be friction in the wheels. It could be air resistance. It could be that this spring isn't quite linear, although we're assuming it is, so that shouldn't matter. But there's error in this. And the only thing that I really want to stress to you is do not put in for the initial values. Even though you know before you release this, V should be 0, it's going to have a value on here. V is essentially 0, but it's actually 0.03. So even though initially V is 0, and then at the end, we're assuming X is 0, they have a value, and they have an error associated with that value. So don't write 0 for them. Actually write what the value is and make sure you take the error. Finally, in the questions, does your experimental data support the theory that the spring is linear? Yes. If you look at your linear I don't know where my thing went. If I look at this, my R-squared value for a linear trend line is 0.999. Really good. That tells me that my data and my linear trend line are, well, that my linear trend line reflects my data almost perfectly. So all I have to say here is the R-squared value of my graph. If it doesn't, if you end up with a weird R-squared value for some reason that's less than 0.99, that doesn't match, and you just say, well, it's not great, and quote your R-squared value always. When you're ever you're asked, does your data, is your data accurate? Quote your R-squared value. So from the measurement, did you conclude that the mechanical energy was conserved in any of the 3 part 2s? All you have to do is look at your percent differences. As long as they're really small, it was conserved. Independent variables are the variables that we set. So we chose in this experiment how far to stretch the string, or the spring, I mean. The fixed variables are the quantities that we assume are held constant. And here we're assuming that K is fixed. Even though it's not, we're assuming that K is fixed. We're also assuming the mass of your device is fixed. The dependent variables are the variables that we find. That is our position and our velocity initially and finally. Okay. In the short conclusion, I want you to, a couple sentences, tell me what the purpose of the lab was. It was to see whether energy was conserved. Then state your findings. State the percent differences you had as numbers, and state the error in your energies to show how accurate it was. So tell me if your energy was accurate or not. Did you have a big error? Did you have a small percent error? And then I want you to talk about where the error came from. This thing got friction in it, right? There's other things that could have affected. Whatever you can come up with that you think affected this thing and made energy not be conserved, cool. And last, how would you improve the experiment to mitigate error? Well, we could do this with a piece of ice on a frozen lake, I guess, to get rid of friction in the wheels. You could do it in a vacuum to get rid of air resistance. I really want you to come up with kind of thoughtful things, but I mean, those work if you can't think of anything. And then how would you do this experiment to learn something more, to learn something interesting? If you can think of something, write that there, okay? So those are the 4 parts of your conclusion. I gave you the data table that you just need to fill out. I gave you the table of results. I showed you how to do each of the calculations and analysis for your errors, other than the LinEst. To do that LinEst, there's a video in the lab report that you can watch. It's really short. Learn how to use LinEst. It's a valuable tool for your other science classes too, so that you know how to find the error in your trend line equation. The other thing is, make sure that you give me a picture of your Excel graph, and it all needs to be labeled correctly. A picture of, just take this and screen capture it for the position and velocity. And I also want a screen capture of the force one that you used. You don't have to do all 3 of the experiments, but you need to give me one of them. Just show me one of them, how you determined what X initial, V initial, X final, and V final were. So just show me a picture. Like if I hit Shift Command 5, I can screen capture that, and I just hit capture and it saves it as a PNG, and then I can put that in my lab report, okay? So that's it. As far as I'm concerned, that's all. This is due the Thursday after our exam. If you want to get started on it before the exam, great. If you want to put it off until the Wednesday after our exam, that's fine too, but it'll be due on that Thursday. I think honestly, it would take about an hour to do, assuming you're on task. It's not really that hard to do. If you want to work with people, have somebody collect the data and get the graphs. And from those graphs, if they write down the X and V's for you, then someone else can do the analysis and the table of results, and a third person can do the conclusion and the questions. And that's a pretty fair way to break this up, I think. Or you can do it by yourself, and I don't think doing it by yourself is too much more work. Obviously, a few of you that don't have your devices, you need to work with someone. So find someone with a device, find a group of people with a device. Let me ask, I know the two of you who don't have devices, do you have people to work with? You found people on the Impulse Lab, right? If you're here. I'm talking to Omar and James. Maybe not. Or no one's listening to me. That's fine. So other than that, I'm going to post this video. Does anyone have any questions about this? And does anyone have any questions about anything else? All right, then. Well,
This is just a general question, but homework 4 is due today. When are you going to post a solution to that?
it's already posted.
Oh, okay.
It's in, I posted homework solutions for, so down here in the quiz solutions and practice exams, solution to homework 1, 2, 3, 4, 5 are there. I'm going to probably post the solution to homework 6. I said I was going to do it this week, but I might do it Sunday morning if I don't do it tomorrow. I'll post the solution to homework 6 and 7 on Sunday, and I'll also post the solutions to these 2 practice exams that I posted. I'll post those Sunday as well. However, tomorrow during our Zoom meeting, I'm going to go through and review energy, which is homework 4 and 5, and collisions and momentum. The types of problems you'll see, and we'll actually talk about the energy momentum problems on those 2 exams. On Monday, we'll talk about the torque problems, the torque and rotation problems. So Monday will be chapter 10, 11, 12, and tomorrow will be 7, 8, and 9. Okay. Other than that, any other questions?
Professor, I've kind of a general question. I don't know if you'd be up for it, but I figured I would ask anyways.
Mm-hmm.
So the lab that's due Thursday, the Impulse Lab, would it be possible for that to, I know we've put off the last one, so would it be possible, could we turn in like the morning after, just because finals for the other summer classes that started earlier are that Thursday?
Okay, so if we want to back that up, and to be honest, it's because I hate grading labs. I need to grade your free fall and vector labs. We can make the Impulse Lab due on Thursday after the exam, if that helps you guys. I don't care. I just want to make sure you do it and that we don't have a big backlog of labs. And I'll make sure that your free fall and your vector labs are graded by this weekend. They'll be graded. I'll probably grade either today or tomorrow. But yeah, I'll put an announcement up that the Impulse Lab doesn't need to be turned in until Thursday, if necessary.
Okay, thank you. Yeah, honestly, any time like is gonna help, just because this week's kind of
Yeah,
swamped.
I forgot about summer early session having finals. I wish.
Yeah, no, it's all good.
But yeah, it's cool. No problem.
Okay,
Just
thank you.
as long as you guys are okay with the lab reports and don't have questions about it, I'm happy to extend it. If you don't want to, if you're, want it extended because you don't know what you're doing, ask me, please. I'll take you through. But does anyone have any questions? Did this lab make sense? I hope. I didn't write this lab, someone else did. And I think it's a little boring, but at least it'll teach you about spring energy versus kinetic energy. So yeah, other than that, I'm done. I'm gonna load this up, and I'll put an announcement up that it's loaded, and an announcement that the lab for Impulse Lab 5 isn't gonna be due until a week from tomorrow. Okay, other than that, I'm done for the day. I put up homework yesterday. get started on it, but it's really, well, yeah, get started on it as soon as you can after your finals are done. And we'll talk about it. You'll have a solution to it on Sunday morning, and we'll talk about it Monday. So, all right, I'm good. If you're all good.
Professor?
Yes, ma'am.
I don't know if you saw the chat, but I was asking if you could explain how to calculate the uncertainty of the mass from the collision data for collision 2 and the lab 5.
Oh, okay. So if I open that up for you, you guys can see my screen, right?
Yeah.
Okay. So I'm opening this up, and you're talking about this part, wherever the stupid thing went. This part right here, right? Do you see that, Caroline?
Yeah.
Okay. So basically, in collision 2 and 3, you had an extra mass. I put my phone in the video on top of it, and then I used pennies. So that's my other mass. And to calculate the mass, we use this. But here's the thing, and I hope the people that left will see this. When we calculate the uncertainty from a function that has multiple variables, we have to calculate the error of each one, square it, and then add them together, take the square root. So how you do that is you take the partial differential of this function with respect to each variable that's a variable in that function. T is, F is, V is, V is, and M other is. So this is actually, I'm sorry, Caroline, this is actually the error for collision 2 and 3. But if you take the partial differential of this with respect to F, all you get is the first term without F. The F just goes away, right? And I show that here. This is the partial differential of this function, of this function, with respect to F, multiplied by the uncertainty of F that you got from your graph, well, that you found, wherever we found it, here, divided by the function again. So when you do that for each, if you just look at this, you get this right here. The uncertainty of the F over F divided by 100%, because you've already figured out what delta F was as a percentage. Delta T over T. And so just all you really have to do, Caroline, is use this equation right here and enter the numbers that you have. This F is your mean. This T is your total time, your delta T. This V final was your mean for V final. This V initial was your mean for V initial. And these were the uncertainties that you found for each of those. The uncertainty in the mass other, you know what? It occurs to me that we didn't have an uncertainty there, did we? Or did we? Oh yeah, we did. I'm sorry. It's right here. So if you calculate this for like the phone or whatever you used and the pennies, it goes in right here. Okay. So you should have figured out what those were. One thing to notice though is that this stuff in the parentheses is just your mass of the IOLAB for that collision. So you can just enter, instead of all this junk here, enter the mass of that you found, your experimental mass. Did that answer your question, Caroline?
Yes, thank you.
Okay. Any other questions, guys? If not, I'm going to end this. Thank you, guys. If you have any problems or questions, text me. Otherwise, I'll see you tomorrow. And tomorrow will last for however long we need it to last.